We have observed that a force is experienced by a current-carrying conductor when kept in an external magnetic field. This was the setup we looked at. Now there are three important parameters in this setup: the magnetic field of the horseshoe magnet, the current flowing in the conductor, and the force on the current-carrying conductor. And what's so special about these three? If we take a closer look, we can observe that all three quantities are at right angles to each other: magnetic field, current, and the force. The legendary scientist John Ambrose Fleming observed the relation between these three parameters. After a lot of research on this relationship, he came up with a rule which helps us in visualizing the direction of the force on a current-carrying conductor when placed in an external magnetic field. It's called the Fleming's left-hand rule. To understand the rule, we first need to understand how the fingers of our left hand need to be placed. So take your left hand such that you're facing your palm and extend your thumb as much as you can towards the left. Fold your left finger and your ring finger and point your middle finger towards yourself. What we have here is three fingers on our left hand mutually perpendicular to each other. In this case, according to the Fleming's left-hand rule, the thumb gives us the direction of the force, the index finger the direction of the magnetic field, and the middle finger the direction of the current. Yes, we need to remember this. Let me repeat it. Thumb tells us the direction of the force, the index finger the direction of the magnetic field, and the middle finger the direction of the current. Let's take a very simple example to understand this. Say we have the North Pole on the left and the South Pole on the right, and in the middle we have a current-carrying conductor. The current is flowing inwards, which means it's flowing away from you. And the magnetic field lines always move from the North Pole to the South Pole. Now, based on Fleming's left-hand rule, can you tell me the direction of the force that will act on the current-carrying conductor? This is how we will be placing the three fingers on our left hand. The index finger in the direction of the magnetic field, the middle finger in the direction of the current, and the thumb, as you can see, is pointing downwards. That's the direction of the force that will be acting on the wire, downwards. Hope this example made the concept a little simpler to understand. Do you remember the experimental setup of our previous video? This is an aluminium rod and this is a strong horseshoe magnet. The current is moving from point B to A and the magnetic field is acting upwards. Can you apply the Fleming's left-hand rule and find out the direction in which the rod will move? If we apply Fleming's left-hand rule, then this is how the fingers will be placed. The middle finger in the direction of the current, the index finger on the direction of the magnetic field, and the thumb, as you can see, is pointing to the left. This tells us that the rod will move towards the left. With these two examples, I'm sure you know how to apply the Fleming's left-hand rule. But do you think it's difficult to remember which finger stands for what? If it's difficult to remember, just relate Fleming's left-hand rule to the FBI. Wait, not the Federal Bureau of Investigation. Here, FBI stands for force, magnetic field, and current. Start from the thumb and go towards the middle finger. Force, magnetic field, and the current. Easy, right? Do you want to try one yourself? Let's go back to the experimental setup. Try to find the direction of force using Fleming's left-hand rule when the current is reversed. Now the current flows from A to B. Will the rod move inwards or outwards? Tell us your answers in the comments section below.